In this video lecture, I'm going to present some of the real-world frequency-dependent behaviors of an op-amp, and we call these AC performance of the op-amp, and they manifest themselves in two realms. One is in the small signal operation of the op-amp, and one is in the large signal. And one of the objectives from this lecture is that you can go into the lab and measure what the AC performance is. So we'll define how we characterize the AC performance. But also, we of course want to know how does the AC limitations, the AC performance of a real-world op-amp actually affect one's ability to use a particular op-amp to design a particular filter or gain function that they're looking to implement. And those will kind of converge when we think about how we can actually measure these parameters in the lab. We'll find that, well, we could try to implement such and such an amplifier, an op-amp amplifier, and the limitations of the op-amp's AC performance will manifest themselves in this particular way. And if we observe that, we can back out of that these AC characteristics, which I will begin now to describe. So you see four bullets here relating to four parameters that we're going to use to define the AC performance of an op-amp, and four parameters therefore that will be in an associated lab, op-amp lab, four parameters that you will extract experimentally for a given op-amp. The first two relate to the small signal behavior of an op-amp. The second two relate to the large signal. So over here I have an op-amp, and I have drawn an output signal. In blue, you see the example of a small signal. So just a reminder, small signal is where the deviations or the changes in the output or the signal are just small deviations from an operating point signal. So the amplitude of the time-varying portion of the signal is small, very small, relative to the DC component of the signal, which is what you see with this signal here. A large signal is one where that is not true, and so here's an example of a large signal waveform. You cannot say that it's operating around any single operating point. It's spanning perhaps a significant portion of the full scale output range that an op-amp can actually operate over. So the first parameter that relates to the small signal behavior of the op-amp, and which will limit the small signal behavior of the op-amp, is the fact that the open loop gain of the op-amp is not only finite, we know that already, but it is now going to be found to be a function of frequency. And as you go to higher frequency, we're going to see that that gain actually decreases. It decreases very nicely, it's well behaved, but it decreases, and we're going to need to model that and then include that when we design some basic op-amp circuit, such as an inverting or non-inverting amplifier, and we expect it to have a gain of 10 or minus 10 from DC all the way up to gigahertz, and in reality it's not going to. It will roll off, the gain will fall from a magnitude of 10 as we go to higher frequency, and we want to be able to predict that. An outcome or a consequence of having a frequency-dependent open-loop gain is that at some frequency, the open-loop gain of the op-amp will no longer be large, like 100,000, but it will actually fall to a value of unity. And the frequency at which that happens, where the open-loop gain is 1, is called the unity gain frequency, or the gain bandwidth product, and there are some other symbols, GBP or FT, omega T. Those are all symbols that are, or terms that are used to describe this frequency. So these two first small signal parameters are not independent of each other. They're related. So if you know one, you can generally derive the other. So the second set of parameters have to do with large signal behavior. And again, those are also, the second one is derived from the first. So the first one is this slew rate, maximum slew rate. So if the output is asked to do something like this, at every point in time, there is a slope, a dV dt. And there is a point at which, of course, that slope is maximum. It looks like it's somewhere in here. And when the question is, any real op amp, do you think it can support any arbitrary high slew rate? Can it slew 10 volts in a nanosecond? Not likely, at least not a general purpose op amp. But maybe it can slew 10 volts or 5 volts in a microsecond. Whatever it is, there is a limit at the rate that the output can actually slew. This is a large signal behavior. It has to do with parasitic capacitances that are part of the semiconductor transistor structures in the op amp, and those capacitances need to have charge deposited on them through currents flowing inside the op amp to keep up in order to support the dV/dt rates. And those currents are limited based on the design of the op amp for power reasons, power consumption reasons, and other things. And so there's a limited slew rate. So when you ask the op amp to put out a signal where the slew rate at any point in that signal is going to be greater than the maximum output slew rate, you will find that the output doesn't keep up with what is requested, and there will be distortion in the signal. So an important thing to keep in mind is that if I say this is group A and this is group B here, we would say that B causes or results in distortion at the output, or distortion of the signal as it gets processed. But A only causes, what do you think? Does it cause distortion? It does not cause distortion. It only causes attenuation. So keep that in mind. This has to do, again, with small signal versus large signal. Now we're going to spend, well, let's do this. I will start with B because it's more straightforward. It's shorter explanation, and then we'll go back to A and look at the small signal characteristic of the op amp. Let's look at, I'm going to define what full power bandwidth is. So suppose we have an input signal VI is equal to some amplitude V MI times sine omega t. Okay, and that goes through some op amp circuit. So it involves an op amp in here. It could be an inverting, non-inverting, difference amp, whatever. And what comes out is VO equal to VMO, so magnitude O output, sine omega t. Now it could have some phase, but we're not even going to care about that. Okay, we're going to ignore that because it's irrelevant in this case for what we're looking at. Okay, we can look at the slope, our time derivative of VO of t. It's going to be dVO of t dt, and that is going to be VMO omega times cosine of omega t. Okay, I'm going to ignore the theta. Okay, the maximum slope is going to occur when cosine is 1 or minus 1. So it's going to be omega times VMO, which we can write as 2 pi times the frequency times VMO. So the point here is to recognize that the demand on the op-amp to produce a high rate of change, okay, and this here is actually slew rate. Slew rate, or SR. The slew rate, the demand on an op-amp to have to produce a certain slew rate at the output is going to be governed, and here we're talking sine waves. Although this is extendable to other signals, we're going to keep it to sine waves. It's going to be dependent not only on the amplitude of the signal you're asking for, but also on the frequency. In other words, you could have a constant amplitude. I have an amplitude of 1 volt. But if I double the frequency that the op-amp is to output, then the maximum slew rate will have doubled as well. Okay, so notice that that amplitude never has an impact on, like when we talk about a transfer function, a frequency response of some filter, we only say that frequency impacts the transmission of that signal, right? How much it's attenuated. Only frequency impacts it. We never say that actually the amplitude would actually impact what gets transmitted. And yet here what's going to happen, once we put a limit on or recognize that the op-amp can only produce a certain maximum slew rate, when we ask for a signal at the output of the op-amp that violates or exceeds that slew rate, we're going to find that there is distortion in the signal. Okay, so we'll define the max slew rate, okay, is equal to just the maximum typically volts per microsecond rate that the op-amp can produce at the output, at its output. Now you could do something like, if you have let's say a non-inverting op-amp, let's even do it just a follower, okay? And if we have VO here and VI, if we put in a step in VI, then what would happen with VO? Ideally, we'd just say it's going to step. Well, it's not. If there's a maximum slew rate, we'll find that it's not going to look like something like this, right? That would be a exponential 1 minus e to the minus t over tau. You're not going to see something like that. You'll actually see something where the slope will be constant. Maybe I'll say this is SR max. Okay, so you will actually see, you'll observe the maximum slew rate of the op-amp by deliberately asking for a signal that you know is beyond the slew rate that the op-amp can produce. So a square wave is a good candidate. Now let's talk about full power bandwidth. Full power bandwidth, we mentioned up here in group B, it derives from slew rate. Okay, and the data sheet for an op-amp may mention full power bandwidth, but it almost always will mention the slew rate. So you can derive a full power bandwidth from the slew rate, and we'll show that now. So full power bandwidth is essentially, in words, let me see, I've got it over here. I'm just going to copy it. And then we'll derive it. Okay, full power bandwidth is the maximum frequency at which the op-amp can output a full-scale sinusoidal signal without exceeding the maximum slew rate. So that's kind of a mouthful. Let's digest that here. So the first thing is we want to put out an output signal that's sinusoidal, and you know that if an op-amp is powered from its power supply rails, and this could be unipolar or bipolar, we're going to assume in this case a bipolar scenario, where we'd call the upper maximum voltage that the op-amp can put out, we'll call that L plus, limit plus, and L minus for the lower one. Now, it turns out that real op-amps will have a maximum output voltage, L plus, that will be less than or equal to the power supply voltage. And here I'm deliberately going to show that it is less than the power supply voltage, VCC, and here we'll say VEE for the negative supply. Now there are some op-amps where they're called rail-to-rail op-amps, meaning that the output can actually go all the way up to the power supply rails, but the ones that, like for instance, you'll be using in lab, cannot attain that. So maybe you supply 10 volts for the power supply rails, but the op-amp may only be able to achieve 7.5 volts or 8 volts before it saturates and the signal gets clipped. So whatever that may be, we define L plus and L minus as the two maximum or full scale, okay, full scale limits for V out. So what we want to do, or the question we're asking is, if I want to produce a sine wave at the output that utilizes the full range or the full capability of the op-amp. So it's going to go from the L minus to L plus, and here I'm assuming that they're both the same, but sometimes one may be in magnitude less than the other, and so it's going to be the lower one that's going to limit this. Then we're wondering, the question is, what is the maximum frequency at which we can put out this amplitude signal without asking the op-amp, or without hitting the slew rate limit? Okay, so this signal here is VO equal to, and the amplitude is going to be, I'll call it just L for the moment, where we will say L is equal to the minimum, in general, the minimum of the magnitude of L plus and the magnitude of L minus. So that just says if one clips at, like say 10 volts, the other one clips at minus 8 volts, then L is going to be 8 volts, because that's what we need to stay within in order to avoid any kind of clipping. So we'll have VO is equal to L sine omega t. Now the max dVdt is going to be equal to omega times L. And we're wondering, what is this frequency? How high can this frequency be such that that maximum slope will not exceed our maximum slew rate? And so we're going to actually set it equal to the maximum slew rate, and we will solve for this frequency. So we'll say it's 2 pi times f, what did I call it? Fm, capital M. You solve for that, we'll find that Fm is equal to the slew rate of the op-amp divided by 2 pi times the limit. In other words, or for example, if L is equal to 8 volts, and if the slew rate for our op-amp is equal to 1 volt per microsecond, then Fm is going to be equal to 8 over 6.28 volts per microsecond. Wait, sorry. Upside down. Okay, 1 volt per microsecond divided by 6.28 times 8 volts. And that equals to 19.9 kilohertz. Now, that does not mean that the op-amp cannot put out a signal that's higher than 19.9 kilohertz. It means, though, that if you want the output to have an amplitude that is going to be plus 8, an amplitude of 8 volts, so from minus 8 volts to plus 8 volts, that the maximum frequency that you can actually generate from the op-amp is going to be 19.9 kilohertz. Above that, and this slew rate here, we'll say the slew rate here is going to be equal to the 1 volt or minus 1 volt per microsecond, right at that, for that signal, that frequency and that amplitude. So that's what we mean by the full power bandwidth. So when you're trying to design or determine what the full power bandwidth of the op-amp is, all you need to do is, instead of measuring this directly, you figure out what the slew rate is of the op-amp, and then you figure out what are the limits. What is L plus and what is L minus? If it turns out that L plus is 9 volts and L minus is minus 8 volts, then you're going to use 8 volts. If it turns out that it's 9 volts and minus 9.5 volts, then you're going to use 9 volts. You put those two together and you can calculate the full power bandwidth from that. And the way that you're going to measure slew rate is that you apply a signal that will demand more of the op-amp than what it can produce in terms of output slewing, and then you observe that. Okay, so now let's go back to our outline here. So we've talked about the large signal AC performance. Now we're going to go look at the small signal AC performance, mainly the fact that the open loop gain is a function of frequency, and subsequently how will that actually affect the closed loop gain of various op-amp circuits, and furthermore, how do we actually measure this frequency dependence of our open loop gain. So let's begin by, let's go back here, frequency dependence of open loop of op-amp open loop gain. So let's review with an inverting op-amp. We have an input VI, we have an output VO, and we know that in an ideal case, this is when the open loop gain is, call it AO, is equal to infinity, that this will be, VO will be minus R2 over R1 VI. Now if it has a finite, if the op-amp has a finite open loop gain, then we will have this expression. It will be minus R2 over R1 over 1 plus quantity 1 plus R2 over R1, and all of that divided by our open loop gain. Now you can see that when A naught goes to infinity, that term vanishes and we arrive at the minus R2 over R1 times VI. Now let's consider an example. Let's say that A naught was only 1,000. Let's say that VO was 5 volts. This would lead to a delta V, which recall VO is equal to A O delta V. So it would result in a delta V of 5 volts over 1,000, or 5 millivolts. Okay, and so we would have 5 millivolts between here and here. Otherwise put, we would say that this node here is at minus 5 millivolts, right? Because the non-inverting input is grounded, and there's a plus to minus 5 volts between the non-inverting and inverting input. So what I want to do, just as kind of an aside, but I think it'll be useful here, I want to resolve this problem with a little different approach. And we can do the following. We can actually use an ideal op amp. Okay, so I put I for ideal, in other words, infinite gain. If we do the following. If we connect a source here at the non-inverting input, and we give it a value of minus 5 millivolts. So if this is an ideal op amp, now the voltage between here, the non-inverting and inverting input, is going to be 0 volts. Right? So from the vantage point of R1 and R2, that non-inverting input, or inverting input, is at minus 5 millivolts, and we want to keep it at minus 5 millivolts. So the only way we can do that is to actually set the non-inverting input to minus 5 millivolts as well, because after all, this is an ideal op amp, and V plus and V minus will be equal to each other. Well, where did 5 millivolts come from? 5 millivolts came from VO over A naught. Okay, so you can actually solve, you can predict the closed loop gain of an op amp circuit having a finite open loop gain by simply adding a voltage source in the non-inverting input of the op amp to an otherwise ideal op amp, and that voltage source at the non-inverting input is given a value of minus VO over A naught. Now I know that looks, you couldn't go build this in the lab because that voltage source is actually a dependent source. It really is, it depends on VO, but it works really well when we just do the analysis. So let's just go ahead and do the analysis. What's nice is you can just write the solution by inspection, so by using superposition. So we'll say VO is equal to, we'll turn off our VO over A naught source, and we just have VI, and that one's easy. It's just minus R2 over R1 VI. Right? Then we have plus, we're going to turn off VI, and now look at the contribution due to the voltage at the non-inverting input, and that will be 1 plus R2 over R1 times this voltage minus VO over A naught. And all of that is equal to VO. So what we need to do is we need to collect VO. So we have minus R2 over R1 VI is equal to VO times 1 plus, what do we have? 1 plus R2 over R1, that whole quantity, over A naught. And now we solve for A naught, and we find that it is minus R2 over R1 divided by the quantity 1 plus R2 over R1 divided by A naught. And that is the same expression that we had up here. Okay, so I just wanted to show you that, because now when we, if we want to look at how does this, how does a non-inverting op amp respond to having a finite open loop gain, we can do that by inspection. So non-inverting op amp. So I guess I'll go ahead and draw it. just so we know the circuit. But we're going to write the response at the output just by inspection using what we just observed above. So again, I'm not going to redraw this, but we would have, what we'll actually have is, let's see, we would have a voltage source right here. Oops. We'll have a voltage source plus minus, this will be minus V over A naught. That will be in series with VI. So we just use superposition. We have 1 plus R2 over R1 VI, and then when we turn off VI, we have 1 plus R2 over R1, and then minus VO over A naught. We collect the terms again for VO, and we will have 1 plus R2 over R1, that whole quantity over A naught times VO, and therefore we'll have VO is equal to 1 plus R2 over R1, the ideal gain, closed loop gain, divided by 1 plus quantity 1 plus R2 over R1, whole thing over A naught, and then all of this times VI. And so very quickly there, then we were able to see how does a frequency, or how does a finite open loop gain affect the non-inverting op amp as we saw for the inverting op amp. Now, we haven't even gotten to the frequency dependence yet, but now we're ready for it. So I'm going to draw a frequency or magnitude plot. We'll do frequency. This will be on a log scale. It's like 1, 10, 100, etc., 1,000, 10,000, 100,000, 1 million, etc. And we're going to plot the gain of our open loop amplifier gain. An ideal finite gain op amp is going to have a gain that's just A sub naught, A0, and it will be that regardless of the frequency. So this frequency scale signifies the frequency of excitation. So if you put in a sine wave to this op amp and you ask the op amp to process that, what will the gain be, open loop gain that the op amp can actually make available? In reality, it is the open loop gain is a frequency function of frequency, and so it'll be actually A of S, and we're going to look at the magnitude here, and we're going to look at the case where, of course, S is J omega, right? J omega or J 2 pi. So this is omega over 2 pi, right? And what we find is that op amps are designed to have, at low frequency, they do in fact have a flat gain that is frequency independent, and they'll call that A naught. But then they actually start rolling off at a constant slope. It's supposed to be a straight line there. And so it's a slope of -1. In other words, 1 decade in gain for every decade in frequency. And the frequency at which it breaks at, this pole frequency, we'll call omega B, or F, I guess in this case will be F sub B. Okay, and so A of S, the actual open loop gain of the op amp, only exhibits an A naught, a DC value, down at low frequency, but then there's a pole that will represent as 1, and the denominator is 1 plus S over omega B. Okay, it's a first order low pass filter, if you will. Now, some example values. Suppose that we have A naught is 10 to the 5. That's pretty realistic. And that, I forgot to define a term here. This frequency where the gain actually crosses unity. Okay, so it's not 0 because this was on a log scale. So 10, 100, etc. So when the gain is actually unity, this frequency here is labeled f of t, or it's GBP, which stands for the gain bandwidth product. Okay, and it's also called unity gain frequency. That's probably the most intuitive one. It's the frequency at which the open loop gain of the op amp is unity. Okay, so let's suppose that the gain bandwidth product is equal to 10 to the 6 hertz, okay, megahertz. What would be the corner frequency FB? Well, if we know that the gain rolls off at 1 decade and gain per decade in frequency, then we can work our way back from our unity gain at 1 megahertz back up here, right? So at 100 kilohertz, the gain would be 10, and at 10 kilohertz, the gain would be 100, and at 1 kilohertz, the gain would be 1,000, and so forth. And so if once we go all the way back to when the gain reaches A0, that will be our frequency FB. And so we can calculate this as follows. FB is approximately the gain bandwidth product times A0. So in this case, it's going to be, say that again, gain bandwidth product divided by A0. So that will be 10 to the 6th hertz divided by 10 to the 5th. So in other words, 10 hertz. We can check this if we say that this is 10 hertz here. And so we have a gain of 100,000 at 10 hertz, which I realize my scale here is not very good, is it? So this would be 10. I don't know if I'm going to be able to do it. That's 1, 2, 3, 4, 5, 6. Okay, 10, 100, 1K, 10K, 100K. So if the gain is 10 to the 5th at 10 hertz, then it's going to be 10 to the 4th at 100, 10 to the 3rd at 1K, 10 to the 2nd at 10K, 10 at 100K, and finally 1 at 1 meg. Okay, and typically the actually data sheets will give you, so data sheets typically provide the gain bandwidth product and maybe AO, but usually not the corner frequency FB, omega B. But yet if you want to model this and use, represent this transfer function, you got to find FB. FB is just simply the ratio of the gain bandwidth product divided by the low frequency or the DC gain. Okay, now notice also that when we say A of S is equal to A0 over 1 plus S over omega B, that this is approximately equal to A0 over S over omega B for S being, or let's say for S over omega B being much greater than 1. Okay, in other words, if we plug in J omega, we'd say omega over omega b is much greater than 1, or omega, frequency of interest here, is much greater than omega b. So this is saying that if we're working at frequencies that are much greater than f of b, which we just found in our example, was 10 hertz, right? 10 hertz. Then we can simplify our frequency-dependent open-loop gain to just being equal to, well, I can rewrite it here to something even simpler. It's going to be A naught times omega b divided by s. I can rewrite that again and say that's 2 pi times A naught times f of b over s. But we saw that from up here, we saw, we see that fb times A naught is equal to gain bandwidth product. So we can use that over here. This right here is the gain bandwidth product, or ft. So we can approximate A of s as being approximately equal to 2 pi times the gain bandwidth product divided by s. Okay, now that will be true whenever we're at frequencies that are significantly greater. So we'll say when frequencies are significantly greater than f of b, which is, like it's not uncommon that it's down at 10 hertz or so. This will actually suffice even when we're working at frequencies below the 10 hertz, because what we're trying to evaluate here is how is our closed loop op-amp circuit going to be affected when our 10 to the 5 open loop gain is no longer 10 to the 5. If it's 10 to the 5 all the way out to high frequencies, then we're set. Assuming we've designed an op-amp already, an op-amp circuit that performs very well with a gain of 10 to the 5. Where we have to be concerned is when we get to frequencies that are well above FB and our open loop gain of the op-amp is no longer 10 to the 5, but it's 10 to the 4, 10 to the 3, 10 to the 2, 10 to the 1. What happens then to the closed loop gain? So all that to say that we're going to use this model right here, or this transfer function, for our open loop gain when we go back and plug that in to our inverting and non-inverting op-amp circuits that we were just looking at a little bit ago. So that's what we're going to do now. Let's go to the inverting op-amp. I'll copy this. So A of S effect on inverting op-amp. So we're going to replace this A naught, we're going to replace that with A of S being approximately equal to, well, we have 2 pi gain bandwidth product, or the other way we can call this here is also 2 pi ft. We use that, and I'm going to just call this omega t for the moment, okay? So we'll say omega t over s. So what does that give us? We have minus r2 over r1 times, and I'm going to write this separately, 1 over 1 plus, okay, 1 plus r2 over r1 divided by omega t over s. This can be rewritten now as 1 over 1 plus s times actually I'm going to rewrite it this way, S over, and I will call this omega breakpoint closed. Okay, so we had omega b, remember when we did the open loop gain, we had FB or omega b, that's the break frequency. That was for open loop. Now we're going to see that we have a break frequency, but it's closed loop, so I put a C. Okay, and this is where we find that omega BC is just omega t. Remember, omega t is just 2 pi gain bandwidth product divided by 1 plus R2 over R1. Okay, and yeah, so let's look at what VO of S over VI of S, magnitude when S equal to j omega, what does that look like as a frequency response plot? Originally, we would have just had R2 over R1. This is magnitude, right? So I'm not going to do the minus sign. That's what would be ideal if we had constant. This would be AO equal to infinity. We would have, let me chop this up. Okay, then we would have this guy if we had AO was finite but constant. Right? This would just simply be the R2 over R1 divided by 1 plus R2 over R1, the whole thing over A naught. Right? So something smaller than the ratio of R2 over R1. Now we're going to find that we actually have a curve that rolls off from here. And I'll do it this. Oops. Here we go. Okay, and this corner frequency now is going to be omega BC, and it is equal to the gain bandwidth product divided, well, 2 pi times that, divided by the gain 1 plus R2 over R1. Okay, if we look at the this is for this is the inverting, okay, inverting op amp. Let's do this again for the non-inverting op amp. Okay, so we have here, we would have VO over VI is 1 plus R2 over R1 divided by 1 plus R2 over R1 divided by A naught. And this now is going to be replaced with 2 pi, well, it was omega, what do we say, omega t over S. So we'll write this out as 1 plus R2 over R1 times the quantity 1 over 1 plus, and we will see that again we have an S over omega BC, where omega BC is equal to 2 pi times the gain bandwidth product divided by 1 plus R2 over R1. Now if we call this guy here the closed loop, AO closed loop Okay, so the initial and let's suppose that that gain was set to be equal to 100, okay, as an example here. And suppose that our gained bandwidth product was equal to 1 megahertz, 10 to the 6 hertz. Okay, then we would find that omega BC, the closed loop break frequency, is going to be 2 pi times a megahertz divided by this initial closed loop gain of 100. In other words, it will be 10 to the 4th hertz. Okay, so look at this. With a gain bandwidth product equal to a megahertz, if AO closed loop, the initial closed loop gain, R1 plus R2 over R1, were equal to 100, then the break frequency, or closed loop break frequency, omega BC, would be equal to 2 pi times a megahertz over 100. In other words, 10 kilohertz. If we designed our op-amp circuit, our non-inverting op-amp, to have a gain of 10, then the break frequency would be equal to 2 pi 1 megahertz over 10, or 100 kilohertz. If we had a closed loop gain initially of 1, okay, then we would have a closed loop break frequency of 1 megahertz. And suppose that we wanted a lot of gain. Let's say we wanted a gain of 1,000. Then the break frequency would be only 1 kilohertz. And we can show what's going on graphically here. I'm going to draw a frequency magnitude plot first of showing A, the open loop gain, A of j omega, okay, and -1 slope, a break frequency at f sub b, okay. It crosses over here, has a unity gain of GBP or FT. Okay. Now we come along and we design an op-amp, a non-inverting op-amp that's going to have a gain of, let's see, this would be 1, 10, 100, 1,000, 10,000. Okay, well, let's say this was a gain of around 10. What we find is that the response of the op-amp is no longer, of the closed loop non-inverting op-amp, is no longer just this constant fixed, gain of, say, 10. Okay, it's 10 at low frequencies, but then at upper frequencies it's going to roll off, and it starts rolling off at that break frequency. So for a gain of 10, we had a break frequency of 100 kilohertz. Let me redraw this here, and somewhere around here. This was 100 kilohertz, and this was a gain of 10. If we had a gain of 100, this was 100, then our break frequency was actually 10 kilohertz. And we can continue. If the gain was 1,000, we found that it was 1 kilohertz. Okay, so you see this trade-off. There is closed loop gain is traded for closed loop bandwidth, i.e. the omega or F omega BC, or I guess FBC. Okay, so if you want more open loop gain, such as 1,000 here, you're not going to get as much bandwidth in your amplifier. However, if you don't need the gain, say you only want a gain of 10, you traded a factor of 100 in closed loop gain, you gain a factor of 100 in closed loop bandwidth. If you only needed a gain of 1, then we'd be down here, and this would extend all the way out to our gain bandwidth product frequency of 1 megahertz, and then it would roll off, and that's what we saw right here. Okay, so what we can say then is that the open loop or closed loop gain times our closed loop bandwidth is equal to our gain bandwidth product. So for example, if we had an open loop gain of 1,000, as we have right here, then we have a closed loop bandwidth of a kilohertz, right? And that is equal to a megahertz. Oops. And now, now you can see at least graphically how the frequency response of the open loop gain of the op-amp affects the closed loop gain of the op-amp. If we had no frequency, any roll-off in the open loop gain of the op-amp, each one of these would just continue extending. Okay, this would be if A of S was just equal to A naught. Okay, but because A of S is A naught divided by 1 plus S over omega B, there's a pole, therefore at higher frequencies the closed loop gain is going to roll off. So how do you actually measure the omega B here, FB, or how do you measure the gain bandwidth product, FT? I think I mentioned already, let me make sure I related. Yes, so you will be given in a data sheet, you'll typically be given A naught up here, and you will be given the gain bandwidth product, and from that you can calculate FB, which is approximately just simply, what is that, gain bandwidth product divided by A naught, okay? But how do you measure it in the lab? So one way to measure it is, let's say that you design an op-amp that has its non-inverting op-amp with the gain of 100, so this guy right here. And you would expect that, before this lecture, you'd expect that gain of 100 to extend out to frequencies, excitation frequencies beyond 10 kilohertz. What you know now is that actually at some frequency that's going to roll off. So if you build such a circuit and you start taking some data points, and you want to do this in a small signal, so using small signals, we don't want to run into slew rate limitations, okay? Using small signals for VI, okay, sweep the frequency, noting, noting the break frequency FBC right here, FBC, the closed loop break frequency. So keep taking data points, and the break frequency will actually be, this will be at 3 dB, minus 3 dB, relative to 100, if that's what you design, a gain of 100. So when you're down, so 40 dB, you're going to be down 3 dB, so in other words, it'll be at 37 dB. So you'll keep moving the frequency of excitation up until you notice a 3 dB roll-off. I would take data up beyond that, get enough data points that you can, when you plot this, you see there's a nice break frequency and then a straight line that's descending 1 decade in amplitude per decade in frequency. And then you can stop. I mean, you could extend this and keep taking data until you actually had a closed loop gain of 1, like out here. And that would be your gain bandwidth product frequency, FT. But it suffices that if you simply know that if you have a good measurement on where the break frequency is, and you know what the open loop or the closed loop low frequency gain is, so let's say you do measure a break frequency at 10 kilohertz, and you were implementing a gain of 100, closed loop gain of 100, then from that you could calculate that the gain bandwidth product of your op-amp is 100 times FBC, or 100 times 10 kilohertz, or 1 megahertz. So that's how you can measure your gain bandwidth product. With your gain bandwidth product and with a DC measurement of A0, which this you had in lab 2, right? If you put A0 together with the gain bandwidth product, then you can find the break frequency of the open loop op-amp gain. So we'll say A0 you would know first, then you could find the gain bandwidth product 2, and then finally you can calculate the open loop break frequency 3 just by calculating, not making another measurement. And again, the way you're going to get the gain bandwidth product is by noting this break frequency, the closed loop break frequency of some op-amp circuit that has some gain. The higher the gain you give it, the lower frequency at which that break will occur. Now I would stay somewhere, I wouldn't go above probably a gain of about 100 on the op-amp. Some other effects can come into play at that point. So, and again, really critical is that you keep this in the small signal, and that you stay away from the rails of the op-amp. So V out needs to be far away from the L plus or from L minus, so that some nonlinearities due to clipping do not come into effect.